Hi everyone, it is a pleasure to present our new results on a faint companion we discovered around the T Tauri star in the coronal asteroid star forming region, which you can see here in the background with this nice Herschel far-infrared image. I'd first like to thank my collaborators for their help in getting the results I'll be presenting today. So let's dive into it. Where is our object of interest? It is located at the edge of the R CrA dark cloud, which is a region of known ongoing star formation, hence very young. So I may have stayed at this image a bit too long. I may have been in lockdown here in Australia for way too long. But at this stage, what I see is actually a cassowary. We can see here the beak, the head, the long neck of the cassowary, and the weird thingy dangling from the neck. And this makes our object of interest the eye of the cassowary. So what is so special about the eye of the cassowary, also known as a CrA-9? So it is an M0.75 T Tauri star. And what is interesting is that it is surrounded by a transition disk. Actually, the spectral energy distribution of the object is somewhere midway between that of PDS-70 and that of SZ91, which are both known to harbor large cavities, which might be suggestive of the presence of embedded giant planets. So far, there's only a low-resolution image available for the disk, which has been obtained with ALMA at sub-millimeter continuum wavelengths. Another interesting feature of this system is its very young age. So there are several age indicators we can use, and they all point towards an age between 1 and 2 million year olds. So the star is accreting based on its H-alpha emission line, and the extinction is relatively moderate towards this object. So altogether, this makes it for a prime target to search for forming planets that could help us better constrain our models of giant planet formation. So we pointed at this system using the Very Large Telescope, and we first carried out observation using the NACO instrument at thermal infrared wavelengths, and we modeled and subtracted the emission from the star using angular differential imaging. Once we do that, we are left with a point source at about 0.7 arc seconds from the star, which corresponds to about 100 AU physical separation. So this motivated us to follow up the object again with NACO. So 1 year later, we could redetect the point source at the same location. And this motivated us for another follow-up, this time using SPHERE at other wavelengths, using the integral field spectrograph and the IRDIS imager. So in all the data sets, the point source is detected at significant level and at a consistent location with respect to each other. In the IFS image that you obtain after modeling and subtracting the emission from the star using spectral and differential imaging, we can see some potential spiral arms here with possibly the main arm connecting to a point source, which is very interesting, although the spirals are still tentative. So what is this faint point source? There are several diagnostics we can use to try to constrain the nature of the object. And the first thing we can do is to take images at different moments to measure the relative motion of the point source with respect to the star. And when we do that, when we put the relative position of the point source with respect to the star at the 3 different epochs of our observation, we see that they're consistent with each other, and they appear to reject the possibility of a fixed background star as we would have expected the point source to move along this trajectory, considering the proper motion of CrA-9. So this is a good sign. Another diagnostic we can use is basically measuring how much fainter the point source is with respect to the star at different wavelengths and beyond a contrast spectrum. So when we do that, we see that on average, the point source is 1,000 times fainter than the star. You can also see that it appears to be redder than the star, which is another good sign. You can see it is redder because the contrast is deeper at shorter wavelengths than at longer wavelengths. And we can also see from this plot that the 2 measurements we obtain at 3.8 micrometer are discrepant. So two measurements were obtained in 2017 and 2018. So this may suggest some variability from either the star and or the point source. So if it is from the star, it wouldn't be surprising since it is a T-Tauri star. So at this stage, what we want is to convert the contrast spectrum into a flux spectrum to infer more properties regarding the point source. For that, we need to multiply the contrast spectrum to the spectrum of the star. Unfortunately, there is no calibrated spectrum of the star at these wavelengths, so we have to model it. So in that purpose, we implemented a new module for spectral characterization of either stars or planets that works in a Bayesian framework that basically performs an MCMC sampling of the parameters of models we try to fit to the observed spectrum. So I won't go into the details of this new module. I will just highlight the fact that it will be made available in the Vortex image processing package. This is an open source package with routines implemented in Python for high contrast imaging. And it will be made available once our paper is accepted. So we use this new tool, SpecFit, to infer the parameters of the star based on its spectral energy distribution. And so we just focus on the green points here for the fit to the grids of BT settle models. Using the posterior distribution, so we can sample models from those posterior distributions and infer what is the most likely spectrum and the uncertainties we have on the spectrum of the star at the wavelength sampling of the IFS, IRDIS, and NACO observations. And we can then propagate those uncertainties to the spectrum of the point source. So the spectrum of the point source is obtained as this spectrum of the star multiplied by the contrast spectrum I showed earlier. Once we do that, we obtain these black arrow bars here, which we also characterize using SpecFit. So this time we use the BT settle and BT dusty grid of models, which have slightly different assumptions regarding the dust in the photosphere. We see that in either cases, almost all the points are well reproduced by the model. And interestingly, we find a large effective temperature of about 3000 Kelvin for a very small photometric radius of only 0.6 Jupiter radius, which I'll get back to in a second. But at first it looks a bit puzzling. What we can also see from this spectrum is that there is a significant outlier with respect to the models. And there could be another potential outlier at shorter wavelength too. So given the fact that the star is accreting, if this point source is a true companion, it might be accreting too. So we consider the possibility of this being due to a bracket gamma emission line. So we added an extra free parameter in our fit, and we found that the most likely luminosity of the bracket gamma line, if this is indeed the reason for the discrepancy here, would be a luminosity of about 10 to the minus 6 solar luminosities. We can also notice that this potential second outlier lies exactly at the wavelength expected for the Paschen gamma line. So altogether, this suggests that the point source might be accreting, since those hydrogen recombination lines are known at traces of mass accretion in T-Tauri stars. So let's compile together all the evidence we have and discuss the different possibilities regarding the true nature of this object. So we saw from the astrometry that it is extremely unlikely to be a background star. Now, can it be an accreting protoplanet? Well, it is very faint with respect to an M0 star. Actually, the absolute magnitudes are consistent, the near-infrared absolute magnitudes are consistent with what you'd expect for a 225 Jupiter mass planet based on hot start formation models. However, the effective temperature we inferred appears a priori too large for what you'd expect for a planet. And the slope of the spectrum we infer is also relatively blue. Now the radius as well is not what you'd expect. It's actually about three times smaller than what you'd expect for a planet that young in this mass range. We also found the point source to be relatively far from its star, which is not necessarily arguing in favor of a planet, although there have been planetary mass objects at older ages that have been found at such large separation. So the fact that we see some tentative spirals and some tentative evidence for emission lines both argue in favor of this scenario. Now, in particular, if it is indeed an accreting protoplanet, what you'd expect, in fact, is that part of the photosphere would get heated by the accretion shock, as shown in these models presented in June 2015. So you'd expect part of the photosphere to be heated up to 3000 Kelvin, which is interestingly close to the value we found. In that case, it would also explain why the photometric radius we infer is only a small fraction of the radius of the planet, because it would just correspond to the part of the photosphere that is heated. Now, another possibility is that we're actually seeing an obscured binary. This would also be consistent with the fact that the point source is very faint, it has a large effective temperature consistent with an M-dwarf, that we are inferring a small photometric radius, that will be consistent with the fact that most of the light from the binary will be blocked, for example, by an edge-on disk. So this scenario has been suggested for 2 or 3 objects in the literature, although in those cases, polarized light was detected from the source, which is not the case in our polarized light observations. Unfortunately, we didn't find anything at the location of the point source in polarized light. So together, I'd say the question is still open. And since I'm running out of time, I'll just leave you with 2 options for follow-up observation that could disentangle between those 2 scenarios. Thank you for your attention.